Hi, everyone. Hello from Seattle. And I see people from all over. Yes, please mute yourself. If you have any questions during the talk, feel free to ask in the chat window. I keep it open so I can see. I'd like this to be interactive as much as possible. But I do have a lot of content that I want to cover. I prepared like 90 slides or so. I'm not gonna be able to cover everything. We have 1 hour and I want to leave time for questions. So the title of my talk today is NoSQL Data Modeling and the LSM Tree, the log structured merge tree. As I've said, my name is Guy. I'm head of training at ScyllaDB and I'm from Tel Aviv, Israel. This talk is, the level is intermediate to advanced. So I assume you have some previous knowledge. However, if you feel that I'm going too fast or you don't know what I'm talking about, so feel free to ask in the chat window. I'm looking at that. So I lead the training at ScyllaDB. My background is as a software engineer. I live in Israel. And the agenda for today, quite a lot of material that I want to cover. I probably won't reach all of it. I'll start with storage engines in general, talk about 2 different types, and then I'll talk about LSM trees and compaction. And then I will talk very briefly about ScyllaDB, which is a database, a NoSQL distributed database that uses the LSM tree. And I will use ScyllaDB as an example to explain how we implemented the LSM tree in our architecture. And if we have enough time, I'll talk about the read-write path in ScyllaDB, some basic data modeling, and then how the LSM tree comes into practice in our distributed database. And then I want to leave a few minutes for Q&A. Great, so I'll start with a quick question. So what is your current NoSQL status? I wrote here 3 options if you can answer in the chat window. I have not heard about NoSQL. I heard about NoSQL, but I haven't used it. Or I've used NoSQL databases before. If you can quickly answer in the chat window, what's your NoSQL status? I haven't heard about it. I heard about it, but I'm not using it, or using NoSQL databases. If you can take a minute to answer. Also making sure that you're with me and I'm not talking to myself. Okay. Okay, so thank you for answering. I see it's like a mixed result. Most people heard about NoSQL. A lot of people used it, which is great. So thank you for that. So the first topic I'm going to start with is storage engines in general. And I put a quote here from a paper written back in the 70s about the B tree. It's a famous paper. And that says that in order to make good use of the computer resources, one must organize files intelligently, making the retrieval process efficient. Okay, so that talks about the importance of data and database in general. So I'm hearing an echo. If you can please mute yourself. And there are different ways to retrieve the data. Just a second. And database programmers have been working on storage engines for quite a while, starting with SQL, going to NoSQL. I won't go into the details of all the history, but there are quite a few influential papers that were written. From the above paper, there's a quote I put here, a precise definition that says to allow users to store, update, and recall data. And those are the things that I will be talking about when I talk about LSM trees. I'll talk about 2 different approaches for handling that. One is in place structure, and that, as an example, is the binary or binary plus tree. And the second one, which will be the focus, will be out of place updates. And as an example of that, the log structured merge tree. So what are those two approaches? The first one is in place. And that means that if we have data and we want to update our data, so here you can see an example where we have a key and a value, K1 with the value V1 and K2 with the value V2, and we want to insert a new value for K1. So we would simply overwrite the existing data, okay? So that's in place structure. And an example of a database that's using that is MySQL, but there are many others as well. And then what we would have is we would simply have the value replaced. The next option for storage engines is out of place updates. And here we would do something quite different. So again, we have the same data, K1 and V1 and K2 and V2. Again, we want to update the value for K1. However, instead of overwriting the existing value, we would simply write the new value for K1. Okay, so what we can understand from this approach is that data is immutable. And this maybe is not so intuitive. The first time that I heard about this idea, it took me some time to get it. But the idea is that we have a database and we actually don't overwrite data, okay? We simply write the new value and the old value is still kept there. So now we would have two values for K1. One is the old data, the old value V1, and the next one is the new value that we wrote, V3. And you can understand from that when we read the data, it requires the database or the storage engine to understand which is the updated value and return that value and not the old one. And it also requires some kind of background operation, which we call compaction, to reorganize the data and make the query efficient. Okay, so this will be the focus of my talk today. And another influential paper, again in the 70s, so quite a long time ago, called Differential Files. You can Google it if you're interested. It shows how this can be applicable in the real world. And it talks about theory, but you can understand that this concept is not very new. People have been talking about it for quite a while. A good analogy that I like for out-of-place storage engine is think about if we have a book and we found a mistake in the book. So one option would be to fix that mistake and reprint all the books with a mistake fixed. Say there's a spelling mistake, and that would be analogous to the in-place storage engine. However, another option would be instead of reprinting the whole book, is to print an extra page and keep all the errors and corrections on that single page. So we would say on page 332, change the word errata to erratum, okay? And we would have a list of all the changes that were made, and we would have just one concentrated place with all the changes to our data instead of reprinting all the books every time. Okay, so it's easy to understand that there are advantages to this approach and that it would reduce the publication cost in this example. And this can be compared to LSM trees or to in-place storage engines. Great. And that brings me to LSM trees and to compaction, log structured merge trees. So there was, again, another paper published in 1996 called the LSM tree paper. which was published and got it made a lot of waves or influence. And it was based on this paper, databases like Apache Cassandra, ScyllaDB, CockroachDB, RocksDB, Yugabyte, and some others, actually implemented the log structure merge tree into a working database. One of the first projects to make use of this technique was the Lucene search engine back in '99. So 24 years ago. Okay, the advantage of using the log structured merge tree in databases is that we can provide a very high write performance with bounded query performance and space utilization. Okay, so these types of databases shine with different things. I'll talk about it in a bit more, but usually high availability, fast write performance, and space utilization. Okay, so I mentioned immutability, and by having data that's immutable, meaning we don't overwrite stale data, we simply write new data, it's easy to understand that that makes writing faster, right? Because if we write data, we don't have to look for the old data. We don't have to see if it already exists in the database. We simply append the write to something that's called an SS table or a sorted string table. And that's easy to understand that that's very fast. Another advantage that I mentioned is availability. So if the database crashes in the middle of a merge, all the components remain intact, okay? So the crash recovery can just discard the partial components, and that goes together with high availability and recovery, of course. And I'll show an example of this in just a bit. Okay, so I talked about writing simply appending the data and ignoring if that data already exists. Data is immutable. But what happens when we want to query data? So when we query or try to read data, we must find the latest version of that key. In this example, we query the key K1, and then we have to read it from both memory and disk and return the most up-to-date information. And I'll also show an example of how this works in ScyllaDB or Apache Cassandra for that matter. So I mentioned the compaction policy. A compaction policy or strategy defines the shape of the LSM tree. And the policy is composed of 4 main attributes. And these are when we should compact, which data should be compacted, how much data should be compacted at once, and what is the layout or how we should basically lay out the data. Okay, I'll talk about different compaction strategies in just a bit. And here in this slide, we can see a real world example of how this works. So this slide is how data is written to ScyllaDB, to Apache Cassandra, probably relevant for DynamoDB as well. And the way that it works is when we have a write query to the database, data is written to something that's called a mem table. And a mem table is a collection of keys and values. So that's our data. And at the same time, it's also written to a commit log on disk. Okay. Once the mem table reaches a size that's predefined, it will be flushed as it is to an SS table on the disk as well. Okay. The reason we have the commit log is for persistency. So even if the computer crashes, the hard drive crashes, or for any other reason, there's no electricity, we will not lose our data. So memory, of course, is volatile. By having the commit log, even if we have a failure, we can still recover from the crash using the commit log. Okay, and also in terms of performance, it's easy to understand that we just write and append data to the mem table. The mem table is full, we flush it to the disk. So there is a question about, will the recording be available? And I believe it will be available after. The slides will definitely be available. I think the recording will be available as well. There's another question, is this considered a write-ahead log? So I'm not really sure. I don't know, sorry. Okay, so I mentioned the SS tables are immutable, they're written to disk, and once we have a number of SS tables that are on disk, these are merged. This happens in the background as a background process, and the SS tables are merged into one SS table. Great. Okay, so let's see some examples for different operations, starting with how an SS table might look like. So SS table, as I've said, is a sorted string table. And what's important to keep in mind is that it's sorted. So it's sorted based on some kind of order. And we store key value pairs in the sorted order. We have multiple segments, and these segments are immutable. Okay, so that's an example of an SS table. And in LSM trees, we only perform sequential writes. So you might be wondering how our data is actually stored. Usually the underlying data structure is some kind of sorted tree, like a red-black tree or some kind of similar data structure. And once we have enough entries in the tree, we flush that to the disk, as I've said before. And because we have the red-black tree, we can write in a sequential way, which goes together with high performance. Okay. How do we read data? So again, the data is sorted. I won't get into all the details in this example, but we have an index which tells us the offsets of the different segments. And then we know when we try to read data, where pretty much it's going to be. Okay, and we keep that in memory. It's an optimization that many databases use, and then we know the offset of the value that we're looking for. Or we can also know that the value is not there and that it's missing. There is something a bit more advanced called Bloom filters, which I won't go into, and that would basically tell us if the data is not in the database. And that begs the question, what happens when we delete data, right? So I said our data is immutable. We cannot, once data is written, we cannot touch it, we cannot erase it. So what happens when we want to delete data? So the way that it works is by using something called tombstones. And what we do is when we actually, when we actually delete data, what the database does is it writes, say, dog, here in this example, the key dog had a value of 52. And then we receive the query, delete the value dog. Sorry, delete the value for the key dog. So what the database would do is instead of actually looking for dog value 52 and deleting that, as would happen in an SQL database, what happens here is that it writes dog, and then it writes a special character, we call it a tombstone, to mark that the value for dog is deleted, okay? And now if we would get a read request, we would see that the latest value for dog is a tombstone, and that means that the value is deleted. Now, once we would compact the data, we would see that the latest value is a tombstone for dog, And in the new SS table, we would simply not have that key value pair for dog. Okay, so when we do the compaction, we write a new SS table, and we can omit values that are no longer relevant, that were deleted, and that can, of course, save us both space on disk and also performance, because we can let go of those old values that are not relevant anymore. Okay, so I keep talking about compaction. When we do a compaction, we can see an example here. We have the compaction process. As I mentioned, it happens in the background. Okay, so it's triggered by reaching some kind of threshold. There are different compaction strategies. If we have time, I'll talk about a few of them. But basically, once we reach a certain threshold, it can be the size of the SS table. We compact SS tables into a new SS table, okay? And the way that it works is that all segments are brought together into a new segment. And in the example above, we have some values for dog. And the latest value for dog, according to the timestamp, would be the one that we would copy into the new SS table that we created. And we can let go of those old values. Okay, so again, these are sorted. So even though it happens in the background, because they are sorted, we can easily check which values exist, and the compaction, it's a process that takes some computing strength, but because the segments and the SS tables are sorted, it's relatively straightforward to perform it. Okay, so I talked for quite a bit. Just want to make sure you're still with me. So let's do another quick poll question. Are you currently, your company, running a distributed database? And if so, how many nodes are in that database? So the answers are no, we're not running a distributed database, or it can be yes, and pretty much the number of nodes that you're running in your database. So if you can take a minute in the chat window and answer that, it would be great. I also want to see that you're with me. So I see some people are not running a distributed database. Some are running 6 nodes, 20 nodes. Anna is running about 10 nodes. Thank you. 4 nodes. Okay, great. So I see mixed results again. Some people are, and some people, I guess, are interested in doing so. Okay, thank you for the answers. Let me continue with my slides. Okay, so I talked about storage engines in general. I talked about LSM trees and compaction. Sorry, can you please mute yourself? Thank you. And now I want to show a real-world example of how that works in a database. So I'm going to talk about ScyllaDB, very briefly giving an intro to the database. And then I will talk about specific topics within that database. I'm going to be using ScyllaDB as an example, okay? I think that pretty much everything that I will be talking from now on is also relevant for Apache Cassandra, for other NoSQL databases like DynamoDB, but I will be using ScyllaDB as an example for explaining those concepts moving forward. So just a few words about ScyllaDB. ScyllaDB is a NoSQL database. I won't talk too much about the CAP theorem because I assume you already have some knowledge about this, and I don't want to spend a lot of time on this. But if we look at the 3 attributes that we want to achieve in distributed databases: availability, consistency, and partition tolerance. So ScyllaDB, together with Apache Cassandra and Amazon DynamoDB, give preference to availability and partition tolerance over consistency. And we have other examples here. Of course, these are just random examples that I wrote. So MySQL, for example, gives preference to consistency over availability. And you can see other examples as well. The idea here is that there are trade-offs between these three traits, and we have to give preference to some over others. And distributed databases have a lot of benefits, but it's also quite complex. And as usual, there are trade-offs. We don't get any free meals. Okay, so another way to look at NoSQL databases is according to their data model. In the examples I've shown so far, I talked about key value store. So there's a question I see about CockroachDB. In the CAP theorem, I think they would be giving preference to consistency over availability. Okay, so they would be together with MySQL there. So in the data model, if we look at these databases, going from the least complex to the most complex, so some NoSQL databases simply have a key and a value. That's very easy. Those are the examples that I've shown so far. Some examples are Redis and Aerospike. Next, in terms of complexity, is a document store. Examples are MongoDB, Couchbase. And here we have data that's more structured. Think of JSON or XML. And then we have wide column store, which is more relevant for the rest of the topics that I'm going to be talking about. And here we have ScyllaDB, Apache Cassandra, DynamoDB, as well as many others. And wide column stores, you can think about the data as stored in rows and columns in tables. And last, in terms of complexity, so most complex would be graph databases. And here, for example, are Janus Graph and Neo4j, and their data is modeled based on edges and vertices. Okay, so some history and context regarding ScyllaDB. So two influential papers, the Amazon Dynamo paper in 2007 and the Google Bigtable paper in 2006. Again, made a lot of waves. And then Apache Cassandra, an open source project, was developed. Apache Cassandra is a very popular database. I would say one of the top 10 most popular databases. Wide column store, NoSQL, written in Java, has a lot of users, a lot of adoption. And ScyllaDB was developed originally as a drop-in replacement for Apache Cassandra. So many of the concepts in the architecture were the same. However, ScyllaDB was written in C++. It was written very close to the hardware, and that allows it to better utilize modern hardware, things like disks that don't spin, multiple CPUs, and so on, and also avoid problems like using garbage collection and other issues that Cassandra users are familiar with. And ScyllaDB was written around 2015, okay, so 8 years ago. These are some comparisons. I don't want to go into it, but basically, by using ScyllaDB, users get high performance. That means high throughput and low latency with a lower total cost of ownership. If you're interested, you can look at our website and see benchmarks and comparisons and so on. Some of the attributes of ScyllaDB, I mentioned we give a preference to availability over consistency. And that means that even if there is a network failure, some nodes are down, there's an earthquake, a fire, whatever, The idea is that the data will still be available, and that means that the database will still be serving requests. And that's similar to Apache Cassandra. The system is highly scalable, and that means that it runs on multiple nodes, it's distributed, and it's possible to add or remove nodes without any downtime. So think, for example, let's say we have an e-commerce website and Black Friday is coming up. We know that we're going to get more traffic. We can simply add more nodes to our database without any downtime, be able to serve more requests on Black Friday. And maybe after Black Friday, we can scale back down if we don't need that extra power or hardware. Performance, I talked about that. High throughput, low latency, also very consistent. Low maintenance, so different auto-tuning capabilities. And it's a drop-in replacement for Apache Cassandra, DynamoDB, and DynamoDB, sorry. And that means that if you're running Apache Cassandra, you can simply use your application as it is and change the underlying, change just the endpoint configuration to point to ScyllaDB instead of Cassandra, and you'll get a much lower cost and better performance. Okay, so now I want to talk about architecture. Let's see how we are with time. Okay, I want to talk about architecture. And this covers basic topics. I'll try to go through it quite fast. Okay, so I mentioned these are things that I talked about, but I didn't really say what they are. I asked you how many nodes you're running. So a node is basically the database software running on a server. In distributed databases, in ScyllaDB, in Apache Cassandra, it contains a portion of the database content. Okay, so data is replicated, and that means that we have multiple copies of the data on different nodes, and that goes together with high availability, meaning that even if a node goes down, our data would still be available. Another important concept is that all nodes are equal. In ScyllaDB, we don't have leader, follower, anything of that sort. And again, that goes together with high availability. There's no single point of failure. Multiple nodes work together in something called a cluster. In production, we have typically 3 nodes or more. Sometimes it can go all the way to hundreds of nodes. And we think about it as a node ring. And as I've said, data is replicated to the different nodes on the cluster. So partition key. This is an important concept when thinking about our data model. And if we have time, I'll talk a bit more about this. So what happens in the database when we read or write data? What happens under the hood is that we have a partition key. So here we have an example with a row. It has 4 columns, ID, name, address, and phone. And the partition key was defined as the ID. And when we read or write data, what happens is that the database would perform a consistent hash function, also called the partitioner, on the partition key. And according to the hash, it would know which node is responsible for that specific data. Actually, which nodes, because it's more than one node, okay? And it would send that query to the right nodes. And there's the question, is ScyllaDB leaderless, and do you use quorums? So the answer is yes and yes. And I think I'll cover it in just a bit. So each node, here we have 3 nodes. Each node is responsible for a different range of tokens. This is a simplification, of course, but it makes it easier to think about it. I mentioned data is replicated, and that's determined according to something called the replication factor. And the replication factor is something that is configurable. It's defined by the user. It's set for a key space. A key space is basically a container of tables. And if, as we can see in this example, the key space called my key space, which is very original, has a replication factor of 3, then each piece of data will be replicated 3 times to 3 different nodes, okay? This is done automatically. Also, what I showed you before about partitioning data, I'm showing you what's happening under the hood, right? So as a user, you don't have to do anything. You simply query the database, but this is what the database is doing under the hood. And that brings me to consistency level. And there was a question about quorum. So consistency level, also abbreviated as CL, is the number of nodes that must acknowledge a read or a write request, okay? Consistency level is defined per operation, okay? And that means that we can have different consistency levels for different queries. Think, for example, say we have an IoT application and we're using some sensor to write the temperature every second. Okay, that's what we're doing. Every second we're writing temperature, temperature, temperature. So maybe the consistency level of a single write is not that important. So if we miss 1 second, it's not that bad. However, maybe when we're doing a read operation, we want our data to be more consistent, and then we can set the consistency level to be, for example, quorum. And that means that if the replication factor was defined as 3, then 2 out of the 3 replicas or 2 out of the 3 nodes would have to acknowledge the read request in order for the query to be considered successful. And different values for the consistency level, we can define it as 1, just 1 node. Quorum, all would mean that all the replicas would have to acknowledge the read request. And of course, there's a trade-off here, right? Because if we define the consistency level as all, then our data would be more consistent, but it would be less available, because if we have a network failure or 1 node is down for whatever reason, then our database would become unavailable. Okay, so there's always a trade-off. Data centers. So the database ScyllaDB is configured, is built to work with multiple data centers, and that makes sense for multiple reasons. Maybe the first one would be for performance, so latencies. It would make more sense if we get a query from a user in the US to serve that request from the US data center, okay? Just because there is a lag, the distance between the US data center and the data center, say in Japan, there's some distance there, and that would increase the lag. So one reason is for performance. A second reason to have multiple data centers is, again, for availability. Even if one rack in a data center goes down, we can have nodes on different racks, and the database is aware of the topology. And if we have multiple data centers, even if there's, I don't know, an earthquake and one data center fails, the data center in Japan would still be able to serve requests. And then maybe a third reason, which is becoming maybe more relevant these days, is that we might want to keep data in different geographical locations. So maybe users from the US, there's some kind of regulation that says that we cannot take that data out of that country, and then we can keep all their data in the US. Okay, so that's also possible to configure. And also here, data centers are created equal, just like nodes. There's no leader, follower, anything of that sort. They're equal. And when we write data, we can use something that's called local quorum, which means that the data would be updated in one data center and then asynchronously updated to the other data centers. Okay, so just making sure if you're still with me. Another quick question is if you can write where you're from and what you're drinking in the chat window. So for those that missed it in the start, I'm from Israel, in Tel Aviv right now, and I'm drinking mate. Okay, it's good to see that I'm not talking to myself.
Guys, now is the last chance. Any more questions?
So I see people drinking tea, vodka, water, not drinking, people from different places. Great. Okay, so we have about 15 minutes and I want to still have some time for questions. So let me continue with your permission. Okay, so I talked about the architecture. Let me show an example of how this actually works when we read or write data. What happens at the cluster level, okay? So what's the read and the write path? So let's just look at this example and I'll try to explain what's going on in our cluster. So this is a random example, but you can see that we have 5 nodes in this cluster, V, W, X, Y, and Z. And in this example, we have a client. The client wants to write data. In this case, let's call that data 1, okay? And it sends the write request to one of the nodes. Any one of the nodes can accept write requests. In this case, the client chose to send the request to node V. Node V, in this case, is defined as the coordinator node just for this specific operation, okay? And again, any one of the nodes can be the coordinator nodes. In this example, we have a replication factor of 3. And if you remember, that means that each piece of data is replicated 3 times to 3 different nodes. And what happens under the hood would be that node V, if you remember, it would run the partitioner, the consistent hash function on the partition key of the data 1. It would see which 3 nodes, 3 replicas are responsible for that data. In our example, it's nodes W, X, and Z. And node V would send the request to those 3 nodes. Okay, it would pass it on to those 3 nodes. Telling them, please write the data 1. In this example, the write was successful, and we can see that each of the replica nodes now has the data that we wrote. And each one of the nodes sends an acknowledgement back to the coordinator node. Okay, and there was a question about that before. So yes, a client, when writing data, expects to receive some kind of acknowledgement if it was successful or not. In this case, for whatever reason, say there's a network failure, the acknowledgement from node X to the coordinator node, node V, fails, it doesn't arrive. Okay, so only 2 out of the 3 acknowledgements are sent to node V. And then we go back to the consistency level. So in this example, the consistency level was defined as quorum, okay? And that means that 2 out of 3 nodes have to acknowledge the request, and therefore the request would be considered successful. So the coordinator node V would return an acknowledgement back to the client. If in this exact same example, another one of our nodes was down, say, and I see that's also a question. So if another one of our nodes was down, then node V would not return an acknowledgement of success. And then the client would have to choose what they want to do. They could resend that request. They could wait. They could do different things, but they would know that the write was not successful in that case. Okay. I'll skip the read path, and I wanted to talk about data modeling, maybe just very briefly, because we don't have much time. So maybe this is the most important slide here about data modeling. A lot of people coming from SQL, from relational databases, have to sort of get used to how data modeling is done with NoSQL. So typically, when we think about data modeling in the relational SQL world, we think of our data, first of all, and we create the model according to the data. Then we think about the schema. And finally, we think about our application, about our queries. Whereas in NoSQL, generalizing, of course, but true in most cases, we think about our queries first. Okay, so first of all, we think about what our queries would be, and then we think about our data, and then we create the model according to that. So that takes a bit of a switch and getting used to that. And I'll also add that we have a resource that's called ScyllaDB University, and we have different lessons that are recorded, and you can find slides, hands-on labs, actual videos covering the topics that I talked about today on ScyllaDB University. It's completely free. Check it out. It's university.scylladb.com. And all the topics that I'm going to be covering or didn't have enough time to cover are covered there, even more in depth. We have some hands-on labs where you can start a cluster, perform queries, see what happens if a node is down, and so on. Okay, so key space, table, partition, and row. I think I talked pretty much about that. Okay, so in the example of the read and write path, I showed you that the client is connecting to one of the nodes. There are a few ways to do that. One is using the CQL shell, which is just a connection directly to the node. In real-world applications, we typically use drivers, and we have drivers for ScyllaDB and for Cassandra in different languages, Go, Rust, Python, yeah, pretty much anything you can think of. And usually drivers are used to interact with the database. CQL, it sounds like SQL, but it's different. It's the Cassandra query language, and it's a language that allows us to query the database. You can find in our documentation all the details and the different commands and the different things that you can do. So I don't want to spend any more time on that. I mentioned the key space. Different data types. Again, you can have a look at our docs to see this. And again, these slides are going to be available to you. You'll get an email with them after this talk, so you can check that out, and also Scylla University. Collections are supported. Partition key I already talked about. Maybe let's go in the last few minutes that we have. I'll go back to the LSM tree. Yeah, maybe just look at this slide. So this is how data is actually stored in ScyllaDB and Apache Cassandra. So we have a partition, which is basically rows, where we have the partition key, the pet ship ID, and that's has all the different columns. In this case, owner and pet name. We have the partition key, which determines the partition, and we can query according to that. And we also have a clustering key, which allows us to basically it determines the order of the data in the row, okay? And we can also query by that. So of course, choosing a partition key is very important. When we create the data model, we try to achieve high cardinality and an even distribution. And we try to avoid, of course, low cardinality. We try to avoid a situation where there's a hot partition. So I don't know, maybe as an example, probably a state in the US is not a great partition key because there are not that many states and they're not evenly distributed if we think of the number of people in each state. So California or Texas would have many more people than some smaller state. That would probably not be a good partition key. So we try to avoid hot partitions and large partitions. Skipping over this, I mentioned the clustering key, which allows us to sort the data in the table. And let's look at LSM trees in practice. So a few words about this slide. I showed it before. What happens in ScyllaDB or Apache Cassandra when we actually write data? So this is what happens on the server. I talked about what conceptually happens in the cluster, but what happens when we write data? So what happens is that the write is written to the mem table. It's written to the commit log at the same time. And once the mem table is full, according to what we defined, it's flushed onto the hard drive. SS tables in Cassandra and in ScyllaDB are basically files on the system, okay? So those are files you can access. I didn't really mention it, but both Apache Cassandra and ScyllaDB are open source software. They're community-based. You can view the code, you can compile it yourself, you can contribute, and there are different options for running it. One is using the open source version, and there's also using database as a service, so as a cloud service. The compaction happens once we have a number of SS tables, again, according to the compaction strategy. And here are some examples of compaction strategies that are used. One is size tiered compaction strategy, and that's the default one. And that's probably the right strategy for you in 90-something% of the cases. And that compacts based on an SS table size bucket. Time window compaction strategy compacts time windows in buckets. And then that's usually valid when we have data that expires. So it has a TTL or a time to live. And finally, we have leveled compaction strategy, which compacts data into levels. I can probably talk for 1 hour just about compaction strategies. There are different topics like space amplification. So how much space on the hard drive using each compaction would take. There's read amplification. And there are different trade-offs. Again, nothing is for free. So we have to find the strategy that's most suitable for our use case. Okay, and this is an example of size-tiered compaction strategy. So we have a mem table, we write multiple SS tables in one tier, and then we compact that, and it goes on. And once we write a new SS table, we can simply let go or discard the old SS tables. Before I wrap it up, I mentioned Scylla University. So great resource for learning more about NoSQL, about compaction, about everything related in general. It has quite a lot of topics. It's completely free, and you can, it's self-paced, so you can just create the user and start learning. Another useful resource is our community forum. which is a great place for asking questions, having a discussion. I personally get an email about every new question. So if you have a question about something that I talked about today, and I didn't know the answer, or we didn't have time to answer all the questions, feel free to ask in the forum and I will answer that. And again, Scylla is open source. You can look at the code on GitHub or just download it, play around with it yourself. And maybe one last thing is that we're hosting the P99 conference. It's a virtual event taking place in October, a few months from now, but it deals with low latency applications and databases in general. And that's completely free. We have some really interesting speakers that already confirmed, and I recommend you check that out. I put a link there. You can just Google P99 conference or register for the conference. I'm going to be there virtually as well. And that's it. If you have any questions, again, feel free to ask in the chat window or ping me. My details are here. And I mentioned P99, and we're also looking for talented people. We're hiring. So if that's interesting for you, you can look at our webpage. You can write me an email. We're looking for mostly developers and engineers, but also other positions. Some of the positions are remote, and we have offices in Israel, in the US, and in Poland, and also people working remotely in random locations. So the recorded presentation, I'm not sure about the website, but we're going to send you an email with a link to that. Okay, so just look for that email. And that's it. Thanks for joining. I hope this was useful to you. Also, if you have any feedback or any input, I would really appreciate that. Always trying to improve the material and the content, and I hope this was useful to you. So thanks for joining today. Appreciate it. Thanks, everyone.